So indeed, I'm going to talk to you about connecting mCRL2 and Dezyne, and mainly about the challenges and opportunities that we get by doing so. Right, so this, as Rob mentioned, this is joint work with Verum, a bunch of people there, but also Jan Friese Grote, who's in the same group as I am, the formal system analysis group at the University of Eindhoven, and Viggo Wesseling. Okay, so before I want to go into the opportunities that we will get by hooking up, or at least considering hooking up mCRL2 to Dezyne, let's first have a look at why we actually want to do so. Right, so and for that, I'm going to just focus back on some of the things that some of the presenters have been talking about earlier today as well. Right, so we're going to just have a brief look at all the things involved in when you use Dezyne. Right? So the central concept in the Dezyne methodology is essentially the Dezyne model. Right? So Dezyne is a domain-specific language. It's tailored to allow you to model very efficiently some kind of event-driven concurrent systems. Right? So it allows you to specify models of your system in such a way that you don't have to focus on all the tiny little bit of details that you get in the system. So you don't need to take care of any pointers, God knows what, any classes that you want to instantiate or things like that. We just focus on the essence of the design, the behavior that is, so not on the details. Right? Another important thing in Dezyne is actually this notion of stepwise refinement that you get. So Dezyne has a notion of interface, and the interface describes from an external point of view what the behavior of a system is. Right? So you're designing a very complex system, but you don't want to know what all the details inside this particular system are. You want to abstract from the hardware behaviors, right? And you just want to reason in terms of, well, I want to switch off or switch on a device, and I don't want to know from an external point of view how I'm going to achieve all that. Right? So this is achieved using the interface. So you get these blue boxes here at the top. And then if you want to say, well, suppose I have defined my interface at this level, there must be some way of achieving this, and I'm going to achieve that using some slightly less complex software. And you're going to rely on some underlying service to achieve that. And you're going to tell, essentially, how you're going to achieve that service at the top level, how you're going to implement that interface by telling how events that happen here are related to events that will be invoked here on these particular interfaces, and how on these interfaces, if you get some kind of event back into this component, what that will actually lead to in the end on this top-level interface. Right, so that's a very important part in your methodology, and it's kind of structuring the design that you have. Now, these days, domain-specific languages are very popular, and one reason for that is actually that if you have such a model, a very high-level abstract model of your system, you want to generate some kind of source code for that. And this is actually what Dezyne offers, right? So you can generate, for instance, Java or C++, and well, we heard a lot of other languages today, like C#, that you can generate for that as well. But the added benefit on top of what you get from, let's say, ordinary domain-specific language approaches that you get in industry these days, is that there is a notion of formal model there as well, right? So Dezyne, underneath the Dezyne model, there's some kind of formal model which allows you to do all sorts of verification, right? So you can check, for instance, for deadlocks, or you can check for live locks, or you can check for refinement. And there's a bunch of other properties that you can check too. Yeah, right. And the tools will actually tell you, once I find a deadlock, well, I can get a trace to the reason as to why there is a deadlock, and I can try to fix that based on the on the information that I get from Dezyne. Right? And the same applies for live locks. Right? So all these errors that you get are fed back essentially into the Dezyne model, and through that iterative scheme, you can actually improve your designs and you can improve your software. And obviously this works if there is a connection between the formal model that we get here and the source code that you get there. That's actually a challenge as well, to get that correct. Right, so there's a bunch of properties that are specified or that are checked when you press the button verify in your Dezyne environment. So there was refinement in there, and well, let's say roughly a third of you have used the Dezyne and ASD approach before. So you might have a clue as to what the refinement there actually is. The deadlock and the life log are kind of self-explanatory, but the refinement notion that is checked is maybe not so much self-explanatory. So I wanted to go a bit into the details that you get there. It's not going to be a very theoretical talk, even though I'm from university, but okay, I think it's good for the motivation actually of this talk to go into some details. So the analysis that is run in Dezyne is actually based on the analysis that you can conduct using the FDR2 or FDR3 tool set, which is developed in Oxford, and the first incarnation of that tool was already in 1989, which is nearly 30 years ago, right? Is it? Actually, right. So it's based on Hoare's process algebra, communicating sequential processes. And it's kind of a, let's say, high-level language, also intended at the time for specifying systems that communicate and that achieve some kind of reactiveness. Now, the notion of refinement that Dezyne uses is actually inherited from the notion of refinement that is offered in this FDR toolset. It's called failures divergence refinement. So in order, if your design environment tells you you succeed with verification, it will have checked something like failure divergence refinement. Now, I guess many of you have not heard of failure divergence refinement, so even though you get a check mark, you probably don't know exactly what you're checking, right? So what kind of guarantees does this notion offer? Well, I mean, very informally, you could say that refinement as checked by FDR, and thus as checked by Dezyne, tells you that a component may not do anything that lies outside the behaviors as specified by the interface. Okay. So let's have a look at a concrete example and try to understand what that actually means. Right, so sorry for the small font. Probably you can't read it in the back. This is a very small interface, right? It's just there for illustration purposes. And what it does is actually describe the behavior of a component which you can start, and then that starting might actually fail or it might succeed. If it fails, you go back to the initial state, and if it succeeds, you can do, let's say, a scheduled proper shutdown at some point. Right? So for that, we need 3 states. There's an off state, an init state, and an on state. We start in the off state. In the off state, you can do a start event. You can receive that from the environment. From that, you move to the initializing state, and then you rely on some external service, for instance, to tell us whether this initialization or starting actually succeeded or not. Right, so now in Dezyne, you can actually tell if you're in this particular state. I'm in state init. I can either do failed, I can receive a failed from my, let's say, underlying component, in which case I move back to the off state again, or I can receive a success, in which case I move to the state on. Right? And now in general, you would have some kind of lovely behavior in when you're in state on, it will do some sort of productive stuff. Here I just abstracted it and say, well, on shutdown, we move back to state on. Now, mathematically speaking, this actually induces some kind of transition system. This is a graph in which you have states and transitions between states, and it would look something like this, right? So you would have a state called off, you would go to start, then you're in a state init, and in state init, well, this either you move in that direction or in that direction, but you don't have any clue as to which direction you're moving. If you're here, well, then you're unlucky because you move to failed. You move to off through a failed. If you're here, well, you're in state on, and you succeeded with what you wanted. Okay, well, this is an interface, and let's have a look at a particular type of, let's say, component that tries to implement that. Right? So that one is here, and it looks much less complex than the interface itself. And it relies on some kind of underlying service here called act. Right? So it's a component which offers some service which accepts the start, and it either fails or succeeds as well. right? So in this particular service that I provide here, only can offer a fail. Right? So we have two states. We have the off state and we have the init state. And we move from the off state, if we receive a start, we move to state init. And we kind of kick the underlying service and component that say, well, you start. Right? And then in the state init, you start to wait for whether this lower level component started. Right? And if it did, it will report back, and in this particular case, it will only report back that it fails. So this component never really does anything useful. Right? So you can kind of view this as the following transition system. We're in state off, we start the machine. The machine itself internally tries to start the underlying device, and this underlying device can only report back that it fails. Now, my question to you is actually whether this is useful. Right? Is that what you intended when you specified the interface? So who thinks this is okay? There's one person saying it's okay. Right? So there's two persons saying it okay. Okay, good. What do you think the design tool will actually tell you? It will give you a thumbs up, right? It will pass all things, right? So if you compare these, this is your interface, and this is your implementation of that particular interface. And design tells you, yes, this is correctly refined. Now, one can wonder whether this is actually what you wanted to achieve, right? Because here, well, we can now kind of abstract from this component that we have using something that looks more complex. And in the end, the component that we implement doesn't even achieve what we wanted to, probably, right? There's never success. So design currently offers no means to check whether good things, assuming that success is actually good in this particular setting here, that good things happen. And the reason is actually that FDR, which is the underlying analysis tool set, does not support verifying liveness properties. So the property that you want to, let's say, start the machine or some kind of underlying device is kind of a liveness property. We want this to achieve in the end. Right? Now, suppose we could even check for liveness. Let's say we can use a simulator of the design environment, so you can try to, let's say, have a look at the interface, and there you can see, well, indeed, it has this property that if I implement this correctly, this interface, it will have this property that it's possible to start the underlying device. However, if you do the refinement check, that itself just does not offer you enough guarantees, right? So the component itself could have marvelously complex behavior, and the interface could be still something you can understand and reason about. All the properties that you, let's say the properties that you wanted to achieve in the end, are not preserved by the refinement, as the example also illustrated. There's a small detail here, but this is probably just for the one or two persons that took my class in model checking, which I teach at the university. There's some properties that actually refinement does actually preserve, and essentially the entire LTL logic is preserved, but that's just a side note here. So this is actually where mCRL2 enters the picture. Right? So rather than going about and introducing entire mCRL2 from the point of view of syntax and semantics and all sorts of other things that you can imagine that I would do typically at the university course level, I just wanted to give you a brief history of mCRL2 here. Right? So mCRL2, well, there was a predecessor called mCRL. I could even go back slightly further to probably, let's say, 85, 86, where there was CRL, which stood for Common Representation Language, which the underlying idea there was actually that there were brilliant minds in the entire of Europe, and they would come together and define one unifying language that they wanted to specify all these event-driven concurrent systems. And well, that got kind of like ugly in the end. So it became a monstrous language, hugely complex, and semantically, that means if you want to reason about what the behaviors are, if you write down a program in this language, you wouldn't be able to understand, and it would always be contradictory in some sense. Right? So you wouldn't even be able to analyze that. So let's say in the 1990s, Jan Frieser Grote then at CWI, so it's the Center of Mathematics and Computer Science in Amsterdam, together with someone else, started to say, well, okay, this is too much, right? So we're just going to toss out lots of things in this common representation language and just keep the bare minimum that we need to still be able to reason about concurrent event-driven systems, right? But what we need is data in there too, right? So there was the way in which you can reason about data in a formal sense, and there was a way in which you could reason about process behaviors, just like in design, that you could do in the 1990s. Okay, so there was lots of theoretical results, which I'll just skip over, but people would try to use, somewhere close to 95 or so, trying to use these tools and theories and this language to prove that all sorts of communication protocols used in the industry were actually correct, or maybe not correct. Right? And it turned out that you needed tools in the end to do all this. Because things on just writing down pen and paper, writing down the specifications and then computing with that turned out to become too complex. Right? So in '95, the first batch of tools essentially for mCRL appeared, probably only on Sun and Solaris at the time. And by '98, actually, people were able to generate state spaces, but not really able to do much with them. So the lots of effort was invested at that particular time to develop all sorts of 2D and 3D visualization tooling, and this actually keeps on going until this moment, for representing and visualizing the behaviors of your system. Right? So to show you an example, maybe this can be seen. So this is, if you get your system, your design system to become more complex, it will have like 50, 60 or 70 or maybe 80 states semantically, right? So this is like this transition system that I drew. So that becomes complex, and we've got tools that try to visualize that in 2D, and at some point that becomes too much. Your screen becomes black because there's so many states on it. So what we have is tools that actually try to do so in 3D. So you can walk around in your state space and zoom in on spots. So this is just a small one, probably consisting of 50 states or so. But even at that point, you can get some information out of these pictures from about the behaviors of your system. Right? Unfortunately, 50 to 60 states is typically very small these days. So what we get typically nowadays will be anything between 100,000 and, several billion states. And for that, you need different methods. And these were, you get some sort of 3D clustering methods. And you can try to understand your behavior of your system using these types of tools in mCRL2, that is. Right, so these represent the behaviors of your system in some sort of artistic manner. But if you understand this tool well enough, and if you understand the language well enough, you can actually read off all sorts of interesting properties. Like in this particular case, there's a very interesting type of vertical symmetry in the behaviors, indicating that there's probably two different types of data elements which really don't affect the behaviors of the system. Okay, well, then when Jan Friso Grote actually moved to Eindhoven University, this was in the early 2000s, and I was there at the time as well. So development on mCRL2, the successor of mCRL, actually started. So mCRL, even though it had a very nice solid form of foundation, it was not always easy to use because, for instance, one of the annoying things you needed to do there was each time you were specifying your system, you needed to specify what the Booleans looked like, or your natural numbers, right? And this is annoying. So when moving from mCRL, with the mu still there, which you can't typeset in your email program, we moved to mCRL2, which still stands for Micro Common Representation Language, version 2. But we also included all sorts of fancy new built-in data types like Booleans, natural numbers, integers, real numbers, lists, bags, sets, etc. Everything based on mathematical foundations. And in 2004, a new development started. We started looking into model checking. Now, I suppose most of you have not heard about model checking, or at least not in the way I refer to it here, right? So let's just, for the sake of argument, take what Wikipedia actually has to say about model checking, because that will serve for the purpose that I have here. Right? So model checking essentially is the following. So you're given a model of a system, right? And the act of model checking essentially exhaustively and automatically checks whether that model that you're given meets a given specification. Right? So model checking itself is a technique for automatically, that is using an algorithm, verifying whether correctness properties of finite state systems hold or not. Right? In this particular setting, you can think of a model as a transition system, for instance, described by an mCRL2 process, but also described by, let's say, a CSP process from FDR, or a Dezyne model. Right? A specification or correctness property, that is typically in this particular setting, it's very academic. It's, let's say, a logical formula. Right? And it's not just a formula that says P or Q, but it's something that even reasons about temporal evolution, the behaviours essentially, in a very concise manner. And the manner that was chosen in mCRL2 is actually mu calculus, which has got fixed points in there and modal operators and all sorts of nastiness. But it's very expressive. You can express anything you want in it, essentially, as long as it's got to deal with behaviors of your system. Right? Okay, so model checking. Let's just have a look at an example here. So we had this example of the component which complied to the interface that we saw earlier, right? So with the starting of the system and just the failing of it. So suppose we want to do that model checking thing on that particular system. We want to verify whether the system always has a possibility to potentially succeed starting the underlying device, that is. Right? So in model checking in mCRL2, you would write down, for instance, a formula, and this is the only formula I'm going to show you. Right? So what you're going to feed to the computer essentially is the model of this transition system, and you're going to feed it this particular formula, which says, essentially, invariantly, whatever state I reach in my system, I always have the possibility to do a number of actions after which I will be able to do a success action. It doesn't say that it will always happen, but it will say that it will never lose the possibility of doing so. This is a type of property that you will encounter quite often, actually, if you do some kind of hardware verification. Okay, well, you can feed this type of property into an algorithm, a model checking algorithm, and you could feed this particular transition system, and the algorithm will say, yes, this holds, this property holds, and you can actually tell so, right? So if I'm in this particular state here, the off state, there's just, there's this particular path. I can do a start, and then I can move there, and I can do success action, right? And the same reasoning holds if I'm there, and if I'm below here, so I'm about to do a fail, I can still take the fail, do the start again, and then move to the success, right? So you can verify very easily, just by looking at it even, that this property holds. The tool will actually tell you, if you feed this particular transition system, it will fail, right? So this is a way in which you can distinguish, let's say, a correct, refined interface that you got here. So this interface that you have here is correctly refined by this component, but still it will not, let's say, adhere to all the properties that you want, provided that you're able to verify these types of properties in the first place. Okay, well, how am I doing for time? Okay, so there's a bunch of case studies that we conducted with mCRL2. So this was just a very toy example that I showed you. There's the real-life examples that we did, and we carried them out using a bunch of master students or PhD students at the time. For instance, we verified the Stellar Cruiser, let's say solar cruiser a few years ago, all the software that was involved in that one, in that solar-powered car, and found a few bugs, fixed all of them, and in the end, when it was driving in Australia, it only broke down once, and then the software apparently behaved exactly as specified, which was good in this particular case. There was some cruise control issues with one of these trucks at some point, which we were able to extract using model checking. There was a deadlock in a pacemaker, which is kind of ironic. These are just a few examples, right? So there's the IEEE Firewire standard, which is actually not entirely what you want. So I don't know exactly the details in the bugs. And there's the poster child application verifying the control software at CERN, in which I was involved and had a huge European project about. So this is actually 12,000 tons of electronics, right? It's massive. It's 12 meters high and I think 25 meters tall. And it's hidden in a cave somewhere in Geneva, or France actually, somewhere deep underneath the ground. And it's actually trying to detect this Higgs boson, right? It's succeeded, and now it's looking for further evidence of other types of particles that you can find out there. So this system, this is actually what it looks like in reality. If you're there, this tiny pixel over here is a human. So you can actually imagine the size of the thing. Right. So, but we were called in at the time to verify their control system because it showed some kind of anomalous behavior. And this is not surprising, as it was a highly complex machine, right, to control. And in order to control that machine, there were like 27,000 communicating finite state machines trying to master that beast and control it. But essentially, at the top level, it's at start or shut down. That was all. But that needed to be refined to start all the underlying devices that you got there. In the end, we managed to do quite some analysis in this one. What people at CERN had done was actually devise their own domain-specific language for specifying these finite state machines. We were able to read these, transform them to mCRL2, understand how they were communicating with each other, and essentially understand their behavior. And we were able to verify a number of properties on these. Not on the entire machine as such using mCRL2, because you can imagine all the machines, all the finite state machines themselves were very small in complexity. Let's say, suppose they all have 5 states, then still you get 5 to the power 27,000 number of possible combinations of states, comparing to 10 to the power 80 of number of atoms in the entire universe. That's kind of massive. Right? So you can imagine you cannot analyze everything. So we were able to verify a number of subsystems, which revealed a number of issues, failure to change state of devices when commissioned to do so, failure to stabilize the control logic, etc. And on individual levels, we were able to actually, in 1 minute, to process the entire control system for failures to stabilize control logic, life locks, that sort of stuff, we were able to detect. And actually also provide fixes for these. Unreachability of states, things like that. Right, so that was actually quite impressive and nice work to do. So how does all of this actually reflect back on design? Because that's what I'm here to talk about, right? So there could be some mCRL2 goodness for design here, which started actually in 2014 when we were granted a European Union project, some small funding, to explore the connections between mCRL2 and Dezyne. And this finished last year, and at the moment, with the general support of Verum, we're continuing some of that investigations. This has led to us developing a prototype implementation which translates Dezyne to mCRL2. So there's now, on the push of a button, there's a translation to mCRL2, essentially. It supports all the, let's say, previous generation. This morning there were some announcements on new features. We haven't yet incorporated them. We essentially have support for all the language constructs. And these also, in the meantime, have been, this, let's say, translation has been fully formalized and documented, nearly fully documented. And we plan on publishing that at some point. There are some issues though, right? So Verum spent an awful lot of time on optimizing that translation to FDR. And we're trying to mimic that, and we only have, let's say, it looks like we had 2 years mostly, but this was just a fraction of our time that we could spend on this. So we haven't yet fully optimized our translations. And one thing that we're looking into is the recursive functions in Dezyne, which do give us a bit of a headache when doing the translation at the moment. But we have reason to believe that we can actually improve on that translation and then get the same type of performance that you could get from FDR, for instance, at this particular moment, or slightly better at some points or slightly worse in some other moments. The prototype at the moment is just a proof of principle, right? So it would show, it's built in Python, very agile in a sense. It shows the feasibility of model checking design models, right? So you can, with a push of a button, you can feed your design model, it will produce mCRL2 models, and you can try to verify whether, let's say, this particular example that I showed you, whether it meets this condition that you can always, at least at some point in the future, switch on your underlying device or not. So that is now possible. Also, what is possible is that you can get these visualization tools to work for you, right? So you could actually use them in design in some sense, if you wish. Right? But this, we're not yet done, right? So there's a road ahead. mCRL2 itself is not yet a full replacement for FDR2 or FDR3. And the one thing that's essentially keeping us is this notion of refinement, which is officially not yet supported in mCRL2. I'm saying officially and yet. We actually have an implementation at this very moment, so except for it hasn't been tested thoroughly yet, right? And we don't know how it compares to FDR, which has like 30 years of developing purely just on this notion of refinement, right? And we just try to implement it in a few weeks. So it could be that FDR is still slightly quicker on that, and we don't know yet. It seems to be no fundamental problem, though. And all the other checks that you can perform using Dezyne, which are carried out by FDR, seem to be no problem when carried out by mCRL2. But again, we need big test sets to actually conclude, to draw some firm conclusions. Now, there is a big pragmatics issue here. I've shown you this, well, let's say a tiny formula there, and that was actually one of the easiest ones I could imagine. Now, I'm very fond of all these fixed point theories and things like that, but I doubt that you would actually appreciate them. So there's a research question here out there, and that is actually, what is a decent property language, which you here could use, right? Because the language itself allows you to express anything, but if you don't know exactly what you're expressing, then it doesn't add any value, right? So you need like 5 years of training to get really professional in this language, and I suppose that's a bit too much. Then again, this language is so expressive and you can do so many things in it. There's probably some properties you're not interested in at all. Right? And maybe by just removing all these properties, or maybe just by starting bottom up and saying, well, we definitely want this type of property, and we want that type of property, we can find some collection of properties that we ultimately want to support, and maybe in the end also include in the design environment. And this also brings about the question of what type of feedback do you want? So in this particular example in which I said, well, I want the underlying system to start, to always be able to start at some point, to never lose the opportunity. It fails, right? But what kind of counterexample do I give back to you as a user? And now I need to give back the entire system. This was manageable. It was just 3 states or 2 states. Right? But imagine it's 60 states and I give you back, well, it doesn't hold. Here is your state space. Start searching for it. So what kind of feedback do you need there? We don't know. Doesn't need to be visual, doesn't need to be interactive. Right? I would suppose that's it, actually. So any questions?